Hello everyone, welcome to my Your Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is balance a binary search tree. Okay, so according to the problem statement, you will be given the root of a binary search tree, and you have to return a balanced binary search tree with the same node values. And if there is more than one answer, you can return any of them. Okay, and what for those of you who do not know what a balanced binary search tree is, the problem statement further states that a binary search tree is a balanced binary search tree if the depth of two subtrees of every nodes differs at most by one. Okay, so for example, here you can see the depth of two subtrees differs at most by one in both of these, and it is not the case here. So let's try to understand it. As you can see here, the depth here is, you can say, there is no node here, so the depth here is 0. And if you count these nodes, these are at certain depth, so the depth of each node is not differing. Two subtrees of the current node is not differing by uh, at most one, it is more than one. Okay, so and if you see in these two examples, okay, so the depth here was 0 and this side it was 1, so 0 minus 1 is 1. Okay, so and these are at the same depth. Okay, and it's the subtrees of 2 are at the same depth. Okay, so the condition is being satisfied here. So this is what the depth mean here is. Okay, and let's have a quick look at the constraints also before thinking of an approach. So according to the constraints, the number of nodes in the tree will be of range 10 raised to power 4, and there will be at least one node in the tree, and values will be of range 10 raised to power 5 of order, you can say. So how we will be solving this particular problem is, first of all, you will store all the nodes of this binary search tree in a list. Okay, and you will use the Inoder Traversal here. Those of you who do not know what Inoder Traversal is, it is nothing but, first of all, for every subtree you visit the left child, then you visit the root of current subtree. Okay, then you visit the right child of the current subtree. So once you are done visiting uh, these nodes in this fashion, then you will be having all the nodes in sorted order. Okay, so why it happens is because when you do in order traversal of BST, all the nodes come in sorted order. So if you do a in order traversal of any of these, the resulting order will be sorted order. You can try it out by having a dry run, but this is the property of the binary search tree which will be coming in handy here. So we need not to sort this array. This array or the list that we will be using for storing the values of these nodes uh, will be already sorted because of use of this in order traversal. Okay, if you are curious to learn more about in order traversal and its implementations, I will be providing uh, an article's link in the description, then you can definitely check it out if you are not familiar with it. So now coming back to the problem statement, once you have stored all the values, okay, so these ones are extra, we can remove them. Okay, so once you have stored the values, then what you will do, you will mark the indices. After marking the indices, you will be using a two pointer kind of approach. Basically they will be there will be 3 pointers. First of all, this is your start index, the 0th index. Then there will be your end index, the last index. Then you will find the middle index between these two. Okay, this can be find out by uh, adding them and dividing by 2. Okay, so a formula like this can be applied. Okay, so it is nothing but if you simplify this formula, it is nothing but start index plus end index whole divided by 2. Okay, I have just used it to prevent overflow, although it may not happen because the range is not that large. But anyways, it is equivalent to this. Okay, so once you are having the middle index, you will call this as your middle index. Then your whole range will be again divided into two parts. Let's say this comes out to be your middle index, or any index comes out to be your middle index, then the situation will be something like this: start index, then your middle index or mid index, then your end index. Okay, let's change color here. So what you will be doing is, for the mid index you will be forming the current root, current subtree's root. Then you will be left with the ranges of start index. Let's for simplicity call this s index, s index to mid index minus 1. Okay, and then it will be mid index plus 1 to end index. Okay, so you have essentially divided the range of the numbers that were available to form the nodes of the tree into two halves. So the one half is this prior to mid index, and the second half is this next to the mid index, and the mid index will be the current subtree root. So what will be the left node for the current subtree root? So the left node will be nothing but when you will make a recursive call in on this range. Okay, and right of this current subtree root will be when you will make a recursive call on this range. Let's change color again. So this will be your left child of the current subtree roots, and this will be your right child, this one. This range will give you. Okay, and at last you will be returning your root of current subtree, and this is how, by using a recursive function, you will be able to construct a new balanced binary search tree. Why it will be balanced? Because essentially in each step we are dividing the available range in approximately half. So the difference between the depths of the children of a subtree of a node will be at most 1 in this case. So this division of the range into approximately half is ensuring that the BST will be balanced. So let's have a quick look at the implementation. More things will be clear in the implementation. Let's bring the code to the board. Let's take a fresh slide. So this is the code. We can definitely remove this part. This is just for the sake of debugging that I used. Okay, now it is very well adjusted. Uh, this, and we can definitely remove this toolbar also. Before removing it, let's zoom in a little bit. It's, I think it's now fine. So let's remove the toolbar also. Okay, so let's begin discussing what is happening here. First of all, as I talked about the list, node list, you will be adding nodes to this list by using Inoder Traversal. So this is the Inoder Traversal being used to populate the list. This will ensure that the list is having all the entries in ascending order, because Inoder Traversal of BST gives you all the nodes in ascending order. Okay, and ascending order, having ascending order is crucial in order to make a BST from this list, because otherwise we would be required to sort this out. Now we do not require to sort it. Okay, so then what you will be doing here is, once you have the list and all the nodes in it, then you will be using your helper function, which is just this procedure that we talked about, that dividing the range between the half and using the mid index for the current subtree root, and left and right range is for the left and right subtrees. Okay, so when your start index will be greater than the end index, in that case you will know that you have exhausted your range. In that case you will return null. Okay, and if your start index and end index are coinciding, that it means that there is only one node left. Then you will form a new tree node with that node's value, and you will be done with it and you will be returning it. Okay, if these two cases are not there, then what you will do, first of all you will find the mid index, which is by using this formula as we have discussed. Then once you are having the mid index, from that mid index value you will be forming the current root. Okay, then what about the left and right childs of current root? Those will be formed by the ranges left. So this is the left range that will be left. This will be the left of mid index, so it will be something like this, mid index, and then there will be this range. Okay, so this will be forming left child, and this particular one be forming right child. Okay, and then we will update the left and right childs of the current root, and then you will be returning the current root. So it is that simple. This is just a DFS traversal that we have done, and this will help you to balance your binary search tree. And as per the complexities, time complexity wise, since we are visiting each nodes a couple of times only, once for you know populating the list and once for forming the values, so you can say time complexity wise it's order of n. And as per the space complexity is concerned, we are using some space here in the list, so it is order of n, and also the recursion stack will also use up to order of n. If even if we have not used the list, the recursion stack would have to take up to order of n space, where n is the number of nodes. Okay. Although there are other methods also of doing it, those involved do not use of extra space like by use of this list, but they will still be using the recursion stack, so the overall time complexity will still remain same. So those methods involved doing a rotation on certain nodes, so left rotation or right rotation. Okay, try to implement these by on your own if you are familiar with it, and if you are not able to do so, then you may ask for the implementation of these two. uh, I have implemented it by left rotation, so you can definitely ask in the comments if you want the code. Otherwise, the complexities will be similar, so it you know does the job. So I think it should be clear enough. So this is the approach and the overall intuition behind it. I hope this solution walkthrough added some value to your DSA journey of honing your DSA skills. I will see you in the next video. Till then, keep practicing and keep solving more problems. Thank you for watching.